Okay, good morning. Let's continue on the Fourier series. Okay, so we talked about Fourier series, and we have looked at how to decompose a periodic function into a summation of sine and cosine terms. So this is a quick recap right here. Okay. If you have a periodic function g of t, and its period is the t naught, then we can basically write this g of t using a constant term plus a summation of a whole bunch of cosine and sine terms. Okay, so those cosine sine terms are what we call the sinusoidal terms. So those sinusoidal terms, right, depends on the periodic function. Then you can calculate the coefficients an and the bn. If you notice that the sinusoidal term, they all have omega naught in its term. Okay, each term has a frequency which is basically a multiple of the omega naught. Okay. So the omega naught, sometimes we call it basically fundamental harmonic frequency. Okay. The other terms we call it basically harmonics of this one here. Okay, so. So omega naught, okay. Omega naught is called fundamental fundamental harmonic. And the other term, right, it's a sinusoid. Okay, the other terms are all sinusoid. And the other term, sinusoid, has a frequency of n omega naught. Okay. And those terms, okay, whatever the n is, it's an integer. Okay, this is called these terms called the nth harmonic. Okay, the nth harmonic. So that's, if you play music, you probably hear that quite a lot, right? So those are basically harmonic signals here. Okay. How do we calculate this an and a naught, an, bn? These are the three formulas we use, okay, to calculate a naught, an, and bn. Okay. So we have gone through an example in the previous lecture, okay, to show you how to calculate a naught, an, bn. Let me quickly recap this one here, because I need to finish that example. Okay. So this is the periodic function we worked on in the previous lecture. The first step is to identify the period of this signal. And identifying the period is quite straightforward. Wherever it starts to repeat itself, then that's the period. Right? So t naught equal to 2, and omega naught is 2 pi over t naught, which is a pi in this case. Okay. So we calculated a naught, which is 1/2, and an turned out to be 0. And bn turned out to be 1 over n pi 1 minus -1 to the power of n. Okay. So that's the results for a naught, an, bn, if you use the formulas listed at here. Okay. to get these three constants, the coefficients. And I also showed you, okay, if you write down the g of t, okay, expand them out, you get a whole bunch of sinusoidal curves. And you can plot these things. If you plot using number of terms, you can try it. You can use 1 term, 5 term, or 20 terms. As you can see, as the more terms you added onto it, the resulted curve will getting closer and closer to that step function, right? To this square wave. Okay. So if you go to infinite, then you will be exactly the same. So this is basically, right, the original, and then those are the approximations over there. Okay. Okay. So any questions so far? This is what we did in the previous lecture. Okay. Now from here, and I want to introduce a different format for Fourier series, okay, which is called a compact form of Fourier series. So basically, based on this format here, okay, let me rewrite the formula for Fourier series, which is here's the Fourier series, right, using 3 coefficients. Now, if you notice that in the bracket at here, okay, the term inside the bracket is an addition, basically a cosine and a sine, but these 2 terms all have the same frequency. So this frequency at here is n omega naught. It's the same frequency. And this is actually what we did when we learned complex number. And I think also in the tutorial or somewhere in the lecture notes, so I didn't go through the detail, but there are demonstrations. When you have 2 or multiple sinusoidal adding them together, and all of them has the same frequency, like in this case, n omega naught, then you actually can rewrite these 2 terms, or 3 terms, or 5 terms, doesn't matter. You can write them into one single term. So essentially, when you have a multiple sinusoid of the same frequency, summing them up together, you get another signal, total signal, right? The overall signal will have the same natural frequency, not natural frequency. They will have the same frequency, basically. Okay. Yeah. That's you add the cosine 3t plus sine 3t, then you get certain type of signal. And that signal still has the same frequency, 3 over there. Okay. So you can put these 2 terms together at here. So you put them together, you get, when you put these 2 terms together, okay, you get a writing looks like this. And so you're getting writing like this. When you add these 2 terms together, you can write it as a single term. The single term has amplitude, has the same frequency, and then a phase angle. Okay. And Cn at here, okay, is equal to an squared plus bn squared. This phi angle at here is inverse tan bn over an. So overall, basically, my Fourier series, okay, formula can be written in an alternative format, which is this format. I can actually introduce C naught to be the same as A naught, right, to keep the symbol consistent. So instead of writing A naught at here, you can write it as C naught. So then everything is in terms of the letter C, right? Yeah. And this format is called a compact form. This is called a compact form of Fourier series. So why is it compact? Instead of two terms here, you have one term, right? That's why it's compact. The connection between Cn and A and Bn is this. The connection between the phi and A and Bn is this term. And this is also very useful formats. Okay, this Cn in here, as we're going to show you, is almost like amplitude. This is basically amplitude, and phi here is the phase. Okay? So you can plot them on the graph versus the frequency omega. Okay? So let's take a look at for this particular example. Right? For this particular example, what will be the Cn and what will be the phi angle? In this example, we have got A and Bn. We have got A naught already. Okay? So in the previous example, we can calculate, so Cn equal to A naught, which is 1/2, okay, C naught, and Cn is equal to An squared, Bn squared, and the square root. Okay. And An in the calculation of that example is 0. Bn in the calculation of that, it's this term here, right? It's this term. Okay. So when you plug in A and Bn, if this is 0 and this is Bn, so you end up with just absolute value of Bn. Right? So you end up with this one here. Absolute value of Bn, let's take a look at this Bn. The Bn value depends on the value of n. And I think in the previous lecture we summarized when n is a odd number, so 1 or 3 or 5, -1 to the odd is -1. Then 1 minus -1 is 2. So that's 2 over n pi. So when n is odd. Okay. And when n is even, this is a 1, so 1 minus 1 is 0, so then it's going to be 0. So Bn just takes 2 over this when n is odd, and 0 when n is even. So similarly for Cn in this case, it's going to be the same as this. So 2 over n pi when n is odd, 0 when n is even. Okay. So this is your Cn in here. You plug in n equal to 1, 2, 3, right? And then you get different values for Cn. Phi n is inverse tan Bn over An. And that's okay. And that's what? That's basically when you plug in 0 over here, and anything Bn is like a Bn over 0. Okay. And which essentially you're calculating the inverse of infinite, right? Or inverse tan of infinite. And inverse tan of infinite equal to pi over 2. Okay. Yeah. So 90 degree, right? So what's the tan? Tan angle is this. When it's pi over 2, you get infinite. So phi here is a constant angle, pi over 2. Okay. Okay. So then we got Cn, we got phi n. Then we actually can plot our Cn and phi n versus omega. So if I plot Cn, I start plotting from C naught. C naught is 1 over 2. That's when omega equal to 0. So you get 1 over 2 at here. This is sometimes how we plot. We can use essentially a bar. On top of the bar, there's a solid or empty circle here to indicate there is an amplitude at this location. and then keep plotting. When n equal to 1, okay, when n equal to 1, it's what? It's n times omega naught, and omega naught is pi. So n times omega naught, when n equal to 1, we're at omega times n omega naught is n times pi. So when n equal to 1, omega equal to pi. So basically, this is the pi is the second location for omega. For omega equal to pi, or n equal to 1, what's the Cn value? Cn value equal to 2 over pi. That's when n is odd, right? So you get another bar at here, which is pi over 2 over pi. That's slightly higher than 1 over 2. And then when n equal to 2, okay, so technically omega equal to 2 pi. However, when n equal to 2, according to the calculation, it's even, so Cn should be 0. So when n equal to 2, or 2 pi for omega, there's nothing at here for Cn. And for 3 pi, so that's when n equal to 3. At this location, your Cn value will be 2 over 3 pi, right? So n equal to 3. So you draw another one in here as 2 over 3 pi. Okay. And then 4 pi will become a 0 again, right? So you can basically plot all of this amplitude out. Okay. And this one gives us the so-called amplitude spectrum. So this is Cn versus omega. Okay, that's called amplitude spectrum. So what does that mean? Basically, if I give you this g of t, right? In this case, it's this function, this g of t here. Okay. It's a time function. Okay. So that's a periodic time function. And now, with the Fourier series, we actually can get this so-called amplitude spectrum. So you know this periodic function can be written in a summation of sinusoidal terms. And then there's also amplitude associated with each one of the terms, so you can actually plot it out to get this so-called amplitude spectrum. Okay. Yeah. So similarly, you can plot phi n and omega. Then we get the so-called phase spectrum. Okay, the phase spectrum. These are these amplitude and phase spectrums are very useful tools to study signals. So, if you have a time signal, you can actually always, instead of studying it in a time domain, you can also study it using this amplitude and phase information. These two together, right? The two spectrum together. So the amplitude and the phase together are the so-called frequency spectrum of the function g of t. Okay. So frequency spectrum. And this is a completely different way of looking at a signal. Okay, so you're not just looking at the time information, you're looking at the frequency information behind this time signal. Okay, that's a completely different perspective to look at a signal. Okay? Yeah. let's try one more example at it here. Okay? Okay, so let's say we have another g of t at here. And we're going to try to do the Fourier series for this periodic function. First step, identify the period of the function. And the period of function at here is, if you look at the period, what's the period of this function? What's the period of this g of t? It's what? 2 pi, right? So it doesn't matter where you start actually. I mean, if you make it comfortable, you can start from negative pi and back to here. Right, that's repeat. Or you start from 0 and back to here. That's a start repeat. Right. So t naught is 2 pi. Okay. Then omega naught, the fundamental harmonic is 2 pi over t naught, which is 1. So then I can calculate, okay, a naught, okay, and bn, an, and bn now. So the formula for calculating is 1 over t naught, 0 to t naught, g of t dt. Okay, so here's the formula for a naught. Now, in this particular case, I mean, you could calculate from 0 to 2 pi, which is fine, okay, which is also fine. But you can also make use of the properties. So, if you recall that, there's a property, right? If g of t is periodic, then we have the following property at here. So when you integrate the g of t from 0 to t naught, let's put t naught, it's equivalent to integrate this function, okay, by shifting the limit with a. Okay, so it's equivalent of that. And that's the nature of a periodic function. So if I come back to this given periodic function in here, okay. Now instead of a 0 to 2 pi, if I do this, if I let's see, if I let a equal to negative pi, right? If I put a negative pi for a, I should get exactly the same integral. But now this time, because t naught is 2 pi, so the integral limits becomes what? Negative pi to pi naught. Okay. So instead of integrating from 0 to 2 pi, you could also from negative pi to pi. And the reason I'm doing this is because you see from negative pi to pi, it probably looks easier instead of 0 to 2 pi. Okay. It's actually the same. It's not too much of a difference here. Okay, but just give you a different perspective. You can still integrate from negative pi to pi at here for this g of t. Yes.
So how would you know that
because of the observation, you look at this g of t, right? a lot of time you may actually easier to identify the period from negative pi to pi. You can see here, repeat, right? Like this. Yeah. So it depends on how comfortable, you know. This is one period, right? Yeah. And that's why you can see from here is, okay, that's negative pi to pi is one period. Yeah. Okay. And of course, nothing wrong with from here to here, right? That's also one period. Okay. Yeah. So I will do this in this question and here. So A naught, okay, equal to 1 over T naught negative pi to pi, and then g of t dt. Okay, g of t dt. T naught is 2 pi, and when you're integrating from negative pi to pi, and you notice that there's only existence of the function between what? Between negative pi over 2 to pi over 2. So really, you're integrating is just pi over 2, negative pi over 2 to pi over 2. And between this range, the function g of t is 1. Right? And so the results of this equal to 1/2. So that's A naught. And the an is 2 over t naught. And now, again, we'll use negative pi to pi. Right? Sorry. Yeah. G of t times cosine n omega naught t, and omega naught, as we calculated, is 1. Right? So n omega naught t, omega naught is 1, so there's no omega naught at here anymore. Right? And g of t, right, is the value between negative pi to pi. So 2 over 2 pi, you're only integrating from negative pi over 2 to pi over 2. Within that range, g of t is 1, and then you're integrating just cosine omega t now. The results of this integral is 2 over n pi sine n pi over 2. That's the results at here. You can write down the details. When n is an even number, so when n is 2 or 4 or 6, and then even divided by 2, another 2 over 2, you get a pi, so multiple of pi. Sine multiple of pi is 0, so when n is 0, even number, you get a 0. Now when n is 1, 5, 9, 13, okay, if you plug 1, 5, 9, 13 into this, you get a positive 1 out of this. So then you get 2 over n pi. But when n is 3, 7, 11, 15, you get negative 1. So overall you get negative 2 over n pi. So that's an. Okay. And then you can get the bn. Similarly, you get essentially 2 over t naught. Again, it's going to be pi over 2 to negative pi over 2 to 2 pi over 2, so 1 sine nt dt. So this one will turn out to be a 0. Okay, it's a constant 0. Okay. Alternative example. So it's very common for periodic function when you're integrating and you get a lot of sine and cosines, right? And you're dealing with sine and cosine here. Okay. So that's what Fourier series is all about, essentially. Okay. And then you can calculate your Cn, right, from here, an squared plus bn squared. So an squared plus bn squared. Bn 0, so that just give you absolute value of an. Then apparently is going to be 0 when n is even. When n is odd, right? Doesn't matter which odd is it. You get 2 over n pi. Okay. And then you can try phi n, which is tan inverse bn over an. And this time it's just a 0. So a 0 give you 0, right? Yeah. So the phi is always 0. The phase. Okay. Okay. So that's another example, okay, for using Fourier series to find on the periodic function. Now the other thing I want to show you is something you can play yourself. There's a website you can play yourself. Okay. So this website, it's a very interesting website. Hopefully still works. So, sometimes those Java things, they don't necessarily work all the time. There, it does work, okay? Yeah. So this website actually shows you Fourier decomposition for a different type of functions. So for example, you have a ramp function at here. Okay, we call the sawtooth function. Okay. So you can also decompose this sawtooth periodic function using Fourier. And you can actually basically adjust the number of terms. Okay. That shows you with the different number of terms what will be the approximation, right? So the more number of terms, and the more accurate of the approximation. Okay. And it can also square wave, and that's fine too. Okay. Excuse me. And also shows you the magnitude for sine and cosine coefficients at here. Okay. And you can also try magnitude and the phase view. This is basically Cn and phi n, right? And you can also do what? You can also play the sound. Okay, so when you click the sound, you play the sound. Why you can play the sound? Because if you notice what the Fourier series is all about, it's basically a composition of different frequencies, right? Each frequency, in theory, it's a sound. You can play it out. And if you play piano, you have this different notes at here. This is basically the frequency associated with each one of the notes. So when you play a chord, a C major chord, C, E, G, that's as far as I know, okay? And then, right, what do? You're playing C, E, G, these three frequencies together, right? It's like you're adding the three frequencies together. You're adding three signals together. Your three fingers may be pressed with a different string. So that's basically the amplitude. Okay? And incidentally, if you take the ratio between the frequency C, E, G, okay, you'll see there are 4, 5, 6. The ratio is 4, 5, 6. This is why it's actually called harmonic scale. So they're in harmony. So if you play completely three different notes, boom, together, they don't sound as good, right? Yeah. So that's the math between the music. There's much more to that. Okay. So there's a saying essentially. It's not a very accurate saying. It's like when you have a periodic function, right? A periodic function is like a chord, and its Fourier series describes the nodes in that chord. Right? Essentially just like that. So try it out. Okay, this website, it can help you a little bit in terms of understanding. You can even use Fourier series on noise, right? Yeah. So sawtooth, triangle, okay, cosine, sine. Yeah. As a matter of fact, when you have a sine, cosine, you will have actually a precise description of that. Right? You don't need a multiple term. You probably only need one term or two terms. Right? Okay, so that's the part of the Fourier series. We've got two different formats to describe Fourier series. Right? One is the basically the traditional format, and the other one is the so-called compact form. And the last type of formats we're going to take a look at. Another one is called the complex form of Fourier series. A complex form Fourier series. This form of Fourier series sometimes is also called exponential Fourier series. So let's take a look at what this complex form of Fourier series is. Right. Now we need to go back to the Euler's formula. If you recall that, Euler's formula says for cosine omega t, it can be represented with this one. So when you have an e to the power jt, if you recall that e to the power jt is cosine t plus j sine t. Okay? Yeah. And also similarly, if you have a sine t, okay, you have a similar formula. So sine t equal to e to the power jt minus e to the power j negative jt over 2j. Okay. So that's Euler's formula, right? So now I'm going to apply this Euler's formula to the Fourier series formula. Okay. So here's what we're going to do. Now let's consider a periodic function g of t equal to g of t minus t plus t naught. Then the original Fourier series formula is a naught plus here's the original Fourier series formula: a naught cosine n omega naught plus b naught bn sine n omega naught t. Okay. So I'm going to apply the Euler's formula to the two cosine and sine terms. So basically, I'll apply this formula here and here. Okay. So with that Euler's formula, I will get. So cosine n omega naught equal to e to the power of j n omega naught t plus e to the power of negative j omega naught t divided by 2. And then bn here times the sine is e to the power of j n omega naught t minus e to the power of negative j n omega naught t divided by 2j. Okay, so that's basically Euler with the Euler's formula, right? So the t at here is n omega naught t, omega naught t. Okay. Now you look at what's in the bracket. So you have ej omega naught t and e to the power of negative j n omega naught t. So I'm going to group similar terms. I will group all of the e to the power j omega n naught t and all the similar terms associated with the e to the power of negative j n omega naught t. And we get this expression now. So you group all this term together and all of the same term for this term together. So that's what we get. So far so good? Yeah. Oh, I did that A go. Did that E go? So from here, I'm going to let, I'm going to let d naught equal to an, and dn equal to the first coefficient, and d negative n go equal to the second coefficient here. So defining a new symbol at here, dn d negative n, and we'll see why this negative n at here. As a matter of fact, what's the connection between dn and d negative n? The what? There's sign difference here, right? So the sign difference at here in complex number conjugate. So you can write this d negative n as the conjugate of dn. Good? So now we have the so-called, the complex form of this Fourier series. So now we have the Fourier series, which is, keep doing this, g of t equal to d naught and plus n equal to 1 at here. So dn times e to the power of j n omega naught t plus d negative n e to the power negative j n omega naught t, like that. This is called a complex form of Fourier series. Now we can do one more step of simplification in terms of symbol at here. So this form of simplification is, instead of n starting from 1, we can actually basically take off this d naught, let n start from negative infinite. What's in the bracket can be just simply dn e to the power of j n omega naught t. So let's see if this makes sense or not. So always remember what the dn and the d negative n means. If I start from negative infinite, then let's say when dn is negative 100, when n is negative 100, so this is, what's this term now? This is d negative 100 e to the power of negative j 100 and omega naught t, right? So this term exactly it's this term here. So the negative value for n basically includes this term. Positive value of n includes this term. And when n equal to 0, which is this term. So the writing of this, is an equivalent format than as this expression here. So more precisely now, the complex form of a Fourier series is written as this one. And dn at here, okay? dn at here, now technically the dn is this an minus this, okay, over 2. A and Bn we have already obtained, right, from the formula for the Fourier series. So I can substitute A and Bn into this, and with some simplifications you're going to get the expression for dn, which is equal to this one. This is basically your dn at here. So ultimately you have two. This is the formula for the complex Fourier series, and dn can be calculated using this expression. So dn is a complex number, right? That's why it's complex form. Right? And as a matter of fact, as we're going to see here, this part, okay, as we're going to see maybe in the next lecture, this is called the Fourier transform. Okay, Fourier transform. Okay, so I don't have much time left, and I'll show you an example of this complex form, and then we have the last topic, which is the Fourier transform. Okay, and that'll be it for this class. Any questions? Okay.